Okay, I'm going to go over some of the questions and also explain thin film interference, I think, in a more detailed and understandable way. I think this worksheet kind of missed a lot of details and made some things a bit confusing. So the important thing from this, at least the worksheet they gave you, is to just understand constructive interference is when the crests and troughs align, and destructive interference is when the crests and troughs are 180 degrees out of alignment, and so there's interference. And another important detail is that you get an 180 degree phase change at a boundary when the boundary is between two mediums that go from small to a large index of refraction. So from a less dense to a more dense medium, let's say. And kind of the situation that's happening here is that light is coming in, and there are two options. Part of the light reflects, another part enters the medium, penetrates it, reflects off the boundary of the next medium, and then comes back out. And so we get these two different waves. The first wave is just a reflection from the incident wave, and the second kind of went through this path and will have either some phase change or not relative to this one. And so there may or may not be some interference. Maybe this wave, let's say, looks like this, and the wave that comes out here maybe looks like this. And so this would be something, maybe something like that. Okay, that's not great. But the basic idea is the waves can either be in phase or out of phase, and they can interfere destructively. And then kind of the discussion starts about, okay, when does it happen? When do they constructively interfere? When do they destructively interfere? I think the way, at least there are a lot of details here that are left out. I think the important thing, to understand is, what does it mean for, first off, kind of this wave to reflect off the boundary, but also what does it mean for there to be an 180 degree phase shift exactly? And I think we can look at some examples to make sense of that. So the idea is that with reflection, it changes the direction of the traveling wave. So the wave is going one way, and then it encounters the boundary and it reflects and goes the other way. And the reflection, confusingly enough, isn't across, the kind of the transverse direction of the wave, but actually across kind of the longitude. So the wave, is going right, and then it reflects and it's going left. And the way to think about it, I think, is as a traveling wave. So if we were to imagine this wave, it's traveling, and if we were to keep going, if there were no boundary, it would look like this, right? Something like that. This is not drawn to scale. But instead of kind of going to the right, it's going to the left. So it's at the kind of the trough here. And so instead of continuing right, oscillating, it's going to continue left oscillating. So let's look at another example of that. As a contrast, this one ended at a trough. This kind of ends at a midpoint between a crest and a trough. And you notice that the reflection doesn't mean it's the same thing as the thing that came in, right? This kind of looks like as the same thing as that came in, but here the amplitude actually goes down to start, going left. And so what's happening? Well, again, if you think about it as a traveling wave, if this were to keep going, it would look like that. So it's going to continue going down, but instead of going down to the right, it's going to be going down to the left. And that's exactly what's happening here. Now let's look at what it means for there to be a 180-degree phase change. And the important thing to note here is that it's still reflecting, right? It's still changing direction from going right to left as it encounters the boundary. But what's happening is if we imagine a wave, what does it mean for there to be a 180-degree phase change? Well, that's kind of referring to the wavelength, right? So if we have a wavelength, then a 180-degree phase change is half of the wavelength, right? 2 pi or 360 degrees is a full wavelength. So we're basically shifting where the wave is from one point in the phase to another. So from this trough and 180 degrees or half a wavelength to the right, that's going to be the crest. And so the wave we get back is a crest at the start, and it's going to the, as it's going to the right, it's going down, but since it's reflecting, we're going left. Another example of this. So let's say the wave coming in hits at the point in between a crest and a trough. So, well, if we imagine this wave, if we were to continue, 180 degrees later, or half a wavelength later, is at the other midpoint between the crest and the trough. So if this is a half a wavelength, then this is half a wavelength. And so if we kind of look at this is going down, and then half a wavelength later, it's going to be going up. Well, it's going up to the right if we were to imagine it continued, if there was no boundary, but there is a boundary, it's reflecting. So instead of going up and right, it's going to be going up and left. So the continuing of, or the fact that it's going up, that's due to the 180-degree phase change. The fact that it's going left, it's due to the reflection. And the important point thing, again, it's a bit confusing because there are two kinds of reflections you can think about, and it's easy to think when you look at this that it's reflecting over this kind of transverse line. But the reality is that that's just a coincidence. Really, what's happening is there's a 180-degree phase change. And so this kind of example shows that, you don't get a reflection over the transverse line here. You actually get the identical thing, or seemingly identical thing coming out. Maybe even one more example to make this even clearer is, let's say this is like a fourth of a wavelength, or not a fourth, maybe more like an eighth, right? So pi over 4, where 2 pi is the full wavelength. So if we look at, pi radians later, 180 degrees later, or half a wavelength later, we see it ends up at 5 pi over 4. That's the point up here. And it's going down and to the right. I think I made an error here. So I think actually this is going down and to the right. So actually we should end up with something like this. So this is going down and to the right. So when we think about the reflection, instead of going right, it's going to go left. And so it's going to go down and to the left. And this is kind of that halfway point from maximum amplitude from the crest. All right, so assuming kind of you've got a handle on all this reflection and phase change stuff, we can now ask, okay, what are the scenarios where we'll get constructive and destructive interference? I've kind of set up this table to kind of look a bit more in depth into all these cases, because in these cases that they show, they don't consider every scenario, and it's not clear actually. They don't illustrate all the examples where you get constructive versus destructive interference for each number of phase changes. So let's start with the situation where we have 0 phase changes, and let's look at when it's constructively interfering. So there are no phase changes, so it's just doing normal kind of reflection off the boundary, continuing as it would to the left instead of going right. And so let's say we have this input wave, it passes through all the boundaries. And there's one component of the output wave that passes through the first boundary but reflects off the second. And so, this continues downward. And so likewise, this will continue downward, but to the left. And then the reflection, there's no phase change. So again, it's continuing as it would. And so this kind of continues going up and to the right. So instead it's going to go up and to the left. And so if we kind of think about what's happening here, it's constructive interference. These points match up. The phase is, identical. And when is that happening? Well, that happens when half a wavelength, passes through the boundary. Half a wavelength kind of spans the kind of the boundary, the gap between these two boundaries, the gap in the medium, or the length of the medium. And so if we denote that length L, right? So if a length has to be half a wavelength, then 2 times the length, right? Bouncing this way and then back, that's 2 times the path length. That has to be a multiple of the wavelength, right? So this thing's half a wavelength, and then completing, so kind of going to the right, but instead going left, that's going to be a full wavelength. And so any multiple of that wavelength will just kind of give you the same result. And I guess an important point to note here that I'm kind of not being explicit with these formulas is that you want this to be, we're kind of considering the wavelength of the film. So that once the light reaches the film, we want that wavelength, not the wavelength, of the input wave before it enters anything and causes any refraction. And of course, kind of the way I've set it up here, so it's going to be some multiple of the lambda. And so it could be a multiple of 1, 2, or 3, 4, and so on. All right. So now let's think about when it destructively interferes, right? So maybe the best way to think about it to start off is to think about the result we want. So we want an input wave. Well, so we get this input wave, and we know the output wave will be the same, right? Because we just have reflection, or it looks the same at least. It's kind of coming down and moving to the left. And we want an output wave that is going to be kind of a reflection of this, or a 180 degree phase shift off of this, right? So this trough aligns with this crest. And so if we want that result, this wave, it's coming down. We need the wave to come back and be up here. And to do that, we can just realize that for it to kind of meet up, there has to be a middle point. And as this is, if we imagine that there's no boundary, this just continues up and to the right. Well, the reflection just makes it continue up and to the left. And then it meets up exactly with what we want, an output wave that is 180 degrees rotated. And so thinking about this kind of setup, what's happening is that we're saying that we want half of the wavelength to be traversed over the total span of the path length, right? Because if we have half a wavelength, that's an 180 degree phase change. So we want half a wavelength to bounce there and back, which means we get a quarter of wavelength for one direction. And so just writing that as a formula, the total path length going right and left, so twice the distance L, we want that to be some half of a wavelength. And it doesn't matter, it could be some multiple. So we could get a multiple of the wavelength, and that would do the job. So as long as it kind of ends up kind of coming back to this kind of peak. All right. So that's for destructive interference for the case with 0 phase changes where, and in all of these examples, I'm not really considering the actual indexes of the mediums, which is for just for this discussion, it's not too important. But when you're solving a problem, you can figure out how many phase changes there are from, the relationship between whether the mediums are increasing index or decreasing. So going now to the next one, where there's 1 phase change, and let's look at the first boundary. So now we're going to get an 180-degree phase shift for the reflected wave off the first boundary, right? So it's a reflected wave and it's getting an 180-degree phase shift. So what's happening here? So this wave would continue as normal going right, but we want to look 180 degrees later, or half a wavelength later. So that's the crest. And, instead of going right, it's now going left. And if we want constructive interference, we want the same thing to happen. And so again, we can kind of imagine a similar situation where we want to think about what will give us a wave that ends up being constructively interfering. And the way to do this is a similar thing actually to the thing that we saw with the destructive interference actually, which is to do a quarter of the total wavelength through one kind of gap between the boundaries. And so the total would give you there and back half a wavelength. And that way we get an 180-degree phase change. And so the same formula actually applies for constructive interference in the 1 boundary case that we want for the constructive interference in the, the destructive interference in the 0 boundary case. So these formulas are the same, this one and this one. And the situations are very similar. It's just depending on now that there's a boundary here, it's going to cause destructive or constructive interference here instead of a destructive interference here. Now looking for the destructive interference case where there's, a single boundary at the first, or single 180-degree phase shift at the first boundary, and we want it to destructively interfere. So again, it's actually similar to the constructive interference in the 0 boundary case. What we want to happen is we want the output wave to be 180 degrees off the output wave that reflects off the first boundary versus the second. And so if we look at the reflection off the second boundary, right, it's going to come back going down and down and to the right. And so when we do a down to the left here, it matches up nicely to become 180-degree phase shift of the wave that we initially started with. And that's kind of similar thing, exactly what happened here. So this wave, reflects off the first boundary and does a 180-degree phase shift. So that's what we end up with here. And we want kind of the reflected wave off the second boundary to be 180 degrees off of this one. We want it to be half a wavelength off of this one. And the way to do that is to just make sure that the kind of, we want half a wavelength, right, to be spanned across this gap. so that we get back a full wavelength when we do twice that. And so when we get a full wavelength, we'll get the same phase as the input wave, so that it's out of phase with kind of this wave reflected off the first boundary. And so since we want a full wavelength, right, we want a full wavelength to happen between going there and back, so that it's out of phase with this wave that's off the reflected off the first boundary and phase shifted. And so that's writing down that formula. That's exactly what I said. We want there and back, so 2 times the gap, to be a multiple of the wavelength. We just want it to meet up. And again, like I mentioned, this is, a similar situation to this one. Now let's look at the case where the phase shift is at the second boundary. Very similar thing. So to kind of what we've been doing before, but with some differences. So, we have an input wave, and the output wave reflected off the first boundary will be kind of seemingly identical in form and shape. So, it's traveling to the right, down, and if we were to keep traveling, it'd be going up and to the right. But instead of going up and to the right, now it's going to be going up and to the left. And so, we get a same waveform. And if we want it to constructively interfere, we want the same waveform to end up. And so, again, the way to think about it is that we know there's going to be a 180-degree phase shift off this boundary. And so since we want the wave to end up here, if this were to keep going, kind of like drawn here, it would end up here. We want it to end up here, right? And so we need something where it starts, somewhere here when it's going to the left, and it's pi away from the other partition. And so that leaves us with this kind of situation where, or really, this is not great. Let me do it here. So we want it to end up here. We want some partition where it's going to travel to this bottom point so that we end up with the same wave coming out. And so that partition then has to be pi away from another partition, half a wavelength away from another partition. And if you kind of stare at this, and maybe if you want, you can be really detailed and try to do the math, you'll see that what has to happen is we have to travel for this much, for actually a quarter of the wavelength, so that pi away we do the last quarter of the wavelength, and so that it kind of does the same form, so that it's going down and to the right here. So when it's reflected off, instead of going right, it's going to go left. So now it's going to go down to the left. And so this bottom point, this trough, meets up with the kind of the trough of the previous one. And so we get an identical waveform. And so this kind of logic, again, is implying that we want something that's half a wavelength, that's actually phase shifted, so that when we do the 180-degree phase shift, it kind of cancels out. And so we actually want this formula where it's saying that we want there and back to be kind of half a wavelength, or really the better way to think about it is that we want just one direction to be a quarter of a wavelength, so that when we do plus pi, right, so this is a quarter of pi, and then we'll do pi, and then, sorry, I've been saying a quarter of pi, I meant pi over 2. So this is pi over 2, and then plus pi, and so this will be pi over 2 as well, and so in total this would be total wavelength. sorry, just a sec. I want to make sure I'm not messing up here. Yeah, so we want this wavelength, right? We want this wavelength to be half of, or sorry, it is so I was saying a quarter of the wavelength, not pi over 4. So it's going to be a quarter of the total wavelength spanning the gap, right? This is pi over 2 is a quarter of 2 pi, where it's like 90 degrees. It's a quarter of 360. And so, you know, we want it, so L over, or just L would be kind of a multiple of 1/2. I guess the better way of thinking about it is with this formula is there and back, right? So if this is a quarter one way, going back is half. And so twice the gap is going to be some half of the wavelength, and then, you know, we can have any multiple of 1/2, or kind of any multiple of, really not a multiple of 1/2, but rather kind of a half separated by multiples of a lambda, right? So you could have a half, 3 halves, and so on. I think that's kind of the thing they have. Where is it? The thing they're referring to here. So 1/2, 3 halves, 5 halves, and so on. All right. So that's the constructive interference case, which again, you see we're kind of alternating between these two formulas, whether it's we want the wavelength or the gap to be half of a wavelength, or some number offset by a multiple of a half, or just straight up a multiple of the wavelength. And so kind of, again, in that spirit, the similar thing happens here, where, you know, here we want destructive interference. So we have a wave, we know that's coming in as usual, and we know that the reflected wave is going to be the same waveform. And so we want the output to be kind of 180 degrees off of that. And so that means we want it, you know, whatever wave we draw in here, we want it to end up at this crest and to cancel out with this trough. And so kind of thinking about the gap, right, and knowing that there's going to be a 180 degree phase shift, right, we can kind of have this construction where, again, kind of looking at the whole waveform, so we want kind of what comes back here to be 180 degrees off of this, and we know this 180 degree shift is going to be involved. And so kind of a similar partition is happening where we know there's going to be an extra pi that comes in, but we don't want it to be, you know, end up with a full wavelength. We actually want it to be, we want it to end up to be out of phase, right, since it's destructive interference. And so considering a wave like this, right, so this is 2 wavelengths. So this is 1 wavelength, this is 2, and say lambda, 2 lambda, and we know there's going to be an extra pi we get from the 180 degree phase shift, and we want it, let's say, to, sorry, so we want it to match up, so that, you know, we'll end up, you know, we start at a trough and we end up at a crest. So let's say we start at this trough and we want to end up at this crest, right? So we know there's going to be an extra pi, so we can kind of place it here, even though it's kind of out of order. And so sorry, that's a 2 pi. So this would be a pi, right? So the 180-degree phase shift would contribute to that much. And so the rest of the wave has to be a full wavelength that spans this gap. So we can move that pi to kind of here, so that the phase change happens in the middle. And so we get this kind of thing where the start is going to go up. We're then going to get this extra phase change that's going to let us end up here. And now again, we're going up and to the right. Instead of going right, it's going to be reflection. We go left, we get what we want. And so this kind of logic shows us that we want this to be half a wavelength for going one length of the gap, and twice the wavelength if we want, or twice the path length to be a full wavelength, or some multiple of it. And that gives us kind of this equation, which we've again seen before. All right, and now for the last scenario, where both boundaries are contributing phase shifts. And so, again, very similar logic to what we've been doing before. So we start with this waveform. We know we're going to end up with a waveform from the first reflection off the first boundary that is 100 degrees out of phase with the initial boundary. And so if we want a constructive interference, we want to end up with a wave that does the same thing. It's 180 degrees out of phase with the initial. And so, again, if we think about kind of a wave, trying to figure out how to construct this thing, we know there are going to be two phase shifts. That need to happen. Or really, so we know we want a total of 2 pi offset, right? So we know we get a pi from here, from this kind of phase shift, and then we also want another pi to happen. Or sorry, not another pi. So this is going to be out of phase, right? So we want another. We kind of want 3 pi's, right? So we know we're getting the pi from this boundary, and we know we're gonna want another extra pi to be offset from this. And so if I draw that, so let's say we're starting down here. We want to figure out how much of this wave to do. And we know at some point there's going to be an extra pi that happens due to this phase change. And then we want it to go another pi more. Or, well, we know it's going to go some, because we're not sure of that yet, but we know it's going to go some distance more that's the same as this one. So maybe I'll call this x and this x. And so we want this x plus this distance to be out of phase, right? And this is pi. And so we want it to be some kind of, so looking at one boundary then, right? So if this is going to end up being some odd multiple of pi, then these have to be pi as well. And so this is, going one path length, that's going to be half a wavelength. And so going there and back, we'll get a full wavelength. And so we end up with the same formula where we want a path length, a total path length, going there and back, to be a multiple of the wavelength. And so we end up with this. All right, so that's for constructive interference. And now for the very last case of this whole table, we want destructive interference. for a case where there are two boundaries. I think I didn't. Let me copy this in. I think I didn't draw that in here. So, oh, there we go. So we're gonna have two 180 degree phase shifts again. And like in the example above, for some reason I've drawn things incorrectly here. Okay, so this one's going to be reflected, right? So we get an input wave here, and we know it's going to be 180 degrees out of phase, and so we'll get a waveform that's like this. Copy that here. That's what it would look like. So off the first boundary, the 180 degrees phase shift, so at the trough it converts into kind of this crest. And since we want destructive interference, we know we're going to get this, right? Or we want to get this. We want to get something that's out of phase with kind of this resultant wave, but actually in phase with the input wave. And so again, kind of similar logic to what we've been doing before. So we know we're going to get an 180 degree phase coming out of here. And we also want it to be in phase with the input wave. So that means we want the starting point, let's say at the trough here, this is the trough here, to end up at another trough ultimately. And so we know we're going to get an extra pi from this 180 degree phase shift. So again, very similar logic to before, this kind of x and x. You know, we're left with 2x for pi, or for single x, pi over 2. And that means, you know, a quarter of a wavelength for one path length, and a total path length for there and back. We want half a wavelength. And so again, we're getting the same formula where we want half a wavelength, or some offset by a multiple of the wavelength. And that's all there's to it. It's kind of a lot. Kind of study over it. Feel free to, you know, this is a video, so you can go back and look back at the details of what I'm saying. And again, feel free to ask me questions, or maybe you see I'm doing something wrong and point it out. So now I'll look at some of the practice problems. So for this first one, so to keep unwanted light from reflecting from the surface of eyeglasses or other lenses, a thin film of a material with an index of refraction n equals 1.38 is coated onto the plastic lens n equals 1.55. It's desired to have a destructive interference for a wavelength of 550 nanometers because that is the center of the visible spectrum. What is this thinnest film that will do this? So as usual with any physics problems, draw the situation. And by the way, I guess I didn't really mention this, but you know, with these diagrams, they kind of showed them vertically. And I kind of changed them to this kind of horizontal situation because it's kind of easier to, you know, based on our familiarity with, you know, trigonometric waves from, let's say, algebra 2 and trig and calculus, kind of usually think about things horizontally as functions. And so this kind of helps us more easily see, as I've been showing, what it means, for example, for a phase shift. What does it look like for us to be 180 degrees later in the wave? Okay, but going back to this question, so I'm drawing things horizontally, and I'm labeling the mediums. So we start with air, which we can say has index of 1, basically like a vacuum. Close enough, at least. And at least in comparison to other mediums, like this glass and the film. And we see we're getting an increasing medium, or an increasing index for each medium, and that means we're going to have a phase change for each one. So from here to here, we're getting a phase change. So we're going from smaller to bigger, and again, also here a phase change. So we got two phase changes. We know we want destructive interference, and so, you know, you can just look at this table. We want destructive interference for two phase changes, and that gives us that formula. And now we just plug in all the numbers and we'll get our answer. I think this number is wrong, but you can plug in, you can solve for L here, and that's just algebra. I guess also quick thing, I guess in terms of memorization, I mean, so this formula, and this, so for the, between both scenarios of the first boundary, they have the same formulas, and also between the 0 and 2 boundaries, they have the same formulas. So 0 and 2, and so that's kind of the, and also the difference between the 0 and 2 case, or like let's say the evens with the odd, is that the constructive and destructive formulas flip. So that's maybe a way of remembering it. All right, looking at the second question, this one's a bit more perplexing to me in that I think they've not given enough information, or I think they might be confusing something, or maybe I am, but I can kind of show you the logic of what's happening at least, and you can make up your own mind, I guess, based on what I say. So kind of this situation, two 15-centimeter long flat glass plates are separated by a 10 micrometer thick spacer at one end, leaving a thin wedge of air between them, as shown on the right. Alternating bright and dark fringes are observed. What is the spacing between two bright fringes? So, well, if we think about what's going on in this situation, right? So we're going to have varying path lengths depending on, where the light comes in. So if light comes in here, we're going to get this path length. If light comes here, we're going to get a bigger path length to the right. And so these fringes are coming from these varying path lengths. And that means for the varying path lengths, right, we're going to get different scenarios. For one path length, there might be constructive interference. For another, it's destructive. And that's where we're getting these alternating bright and dark fringes. And so, we can ask, okay, so we can now look at the kind of the mediums. So the first medium is air. We can say it's approximately 1. They didn't tell us the index of the glass, but we can just say we know it's greater than 1. And then we go back to air in between here, which is 1 again. And, I guess have I considered everything? So there's, okay, so yeah, this question kind of overall confused me a bit, because actually there's a lot of waves to consider here, but they really are considering the 2 waves down here. So actually, I don't know if this changes much for my later work, but I think looking closer at this, they're just considering the interference between the wave that bounces off this boundary of the glass and this boundary of the glass. So it's actually, and they don't even consider the bouncing off that boundary. Okay, so in that case, I need to fix this diagram a bit. We're kind of neglecting the air here. So we're actually starting off with an index greater than 1, right, in this glass. We get to an index equal to 1. So this is like the glass 1, I'll call it. And this is, or let's say, what's going on? Okay, so let's call this top glass, and this is bottom glass. And then this is the air, kind of, let's say, the air strip, so the air in between. So going from a bigger index to smaller index, we're not going to have any phase shift, but for this situation, this is going to be an index bigger than 1. And so we are going to get a phase shift here, 180-degree phase shift, going from smaller to bigger. And so the reflection that happens here and this one will interfere. So I'll draw it like that. And so ultimately we're considering the interference, as they pop out in the end. And so, if we want to ask what is the difference between when these constructively interfere versus destructively interfere, so this is a scenario where there's one phase shift. And so in both these cases, the difference is that in the constructive case, we get this formula. In the destructive case, we get this formula. And so this formula is for the constructive case, where there's one phase change. And this formula is for the destructive case, where we also want, we get one phase change. And so we can ask, okay, so what's the difference in path lengths, right? What's the difference in path lengths between destructive and constructive cases? And, I think I'm realizing I've messed up something here. But we want, but let's not worry about that for now. So if we look at the difference between the path lengths, we get this 1/4 lambda, right? So L1 minus L2, just some algebra, you get 1/4 of the wavelength. And just this alone already, we need the wavelength, and they've not told us it, which already kind of poses a question of, whether they're missing something in this question. But kind of looking at the geometry of the situation, right? So I think I've drawn things wrong here. So we want the difference actually between this length and this length, right? So this is this triangle here, that's the air gap. And then this is the glass, and then this is the air up here again. So this air gap, right? So we want these kind of lengths here, these path lengths, to be at a difference of 1/4 of a wavelength. And this would be just kind of like a similar triangle geometry problem where, I don't know, let's say this path length with respect to, let's say, okay, so the proportion, so we know it's T over L. So that's kind of for these sides of the triangle, so the big sides here. So this 10 micrometers and this 15 centimeters. And that's going to be equal to, some, let's say we have some T, right? So that's going to be in proportion to some, I don't know, some other L1. So let's say this is T. And there's going to be some L1 here, and that's going to be in proportion to, let's say, a difference in the wavelength, or a difference in the path length. So we want T plus delta L. And we can ask, okay, how does that affect this length, right? Because that's what they're asking for. Because the difference in these lengths, the difference between this path length scenario versus another path length scenario horizontally is kind of the distance between the fringes that they're asking for. So a T plus delta L, so a different point, let's say this one, we're going to ask, okay, what is that horizontal length? Well, okay, so it's going to be some delta as well. So let's say L1 plus, this is a lowercase l. This is going to be a capital L for the bottom. And so we could solve for this delta L, and that would just be some algebra using this proportion, since these are the knowns. But again, this delta L that we care about will be a function of this delta lowercase l, of the difference in the path lengths, and that one depends on the wavelength, like I've shown in this formula. So I don't quite see how to resolve that. We just need the wavelength. Different wavelengths will cause different distances between fringes, as far as I can tell. Let's see, so if I were to solve for delta L, I mean, we get like a system of two equations here. And and we have a system of two equations, right? So if I draw it out, so T over L equals T over L1. That's one equation. The other one is, let's say, T over L1 equals this thing. Oh. And, okay, so what are the unknowns? Well, I mean, we could just pick some t, so t wouldn't be an unknown. So this would not be an unknown. So maybe I'll kind of highlight all the unknowns. So, oh yeah, I guess, So if we pick some t, maybe that resolves it. So if we just pick some t, let's see. Okay, well, okay, so we pick some t, right? So these are known. So the t can become known, and then the L1 can become known. So this would all become known. But now we have two unknowns here. We still have two unknowns. We have this delta L and this lowercase delta L, right? So these would be the two unknowns, and so we still end up with one equation with two unknowns, and so we need another equation. And I think that other equation has to happen from knowing the wavelength of the light so that we can determine the path length. And assuming we do know the wavelength, then kind of this geometry I showed here, that comes from Snell's law, which we don't have to go into too many details, but it kind of tells you how the angle changes. And basically, the ultimate angle change, since we know it's going to be back in air, it's going to be the same angle as the initial angle in the air. Yeah, and I think that's all there is to that. I think really this ultimately is independent. Maybe this is wrong to say. Maybe it's not independent of L and T. Now that I've realized there's that I kind of mislabeled thing. So it is dependent on L of T, but really what we want to say, it's also depends on the wavelength. So I would argue that there's not enough information to answer this question without just using variables, which we could do. Again, it's algebra. Just plug in this formula for L in terms of lambda, or the delta L in terms of lambda, and you could solve for this capital delta L. Okay, moving on to the next one, which is a bit more straightforward. So determine the frequency of light in the air. They give us this wavelength. Do the speed of light over the wavelength. That will give you the frequency. What are the wavelength, frequency, and speed of light in a film? So we know the frequency is going to be the same. This kind of comes from the fact that the ratio of velocities, if I remember correctly, is the ratio of the indexes. And so and then using that relationship, we can come to the conclusion that the frequencies need to be same. Yeah, C1 over C2, I think that ratio is the same thing as N1 over N2. Yeah. Whatever, that detail doesn't matter too much. You can just remember that frequency is the same, and so you can solve for also the wavelength in the film. And, they give us the index, so this is kind of just definitional. The wavelength coming in over the index, that's going to give us the resultant wavelength. And so that's just this. You can evaluate that. And, taking those two together, we have the wavelength. We know the frequency from the previous question. You can multiply those together, get the speed of light. Now, for the next question, they're asking for the interface 180 degrees phase change. Well, looking at this situation, we get an increase going from the first to that middle film layer, and so that's when we'll get the phase change. So we'll be at the first boundary. Not at the second, because from the second to the third, we have a decrease in the index. All right, looking at the next question, they're asking what is the minimum thickness of the film that will result in constructor interference. This is pretty similar to the first question. We just figure out the formula. We have one boundary. We want constructor interference. So we want this formula. The same formula that we saw before that actually works for both scenarios where we get a phase change at the first or second boundary. And so this is the formula you use, or oops, up here. And so you can, and also make sure to solve for the wavelength of the film. Which actually I guess I didn't talk about, but what you want to do here as well, which is do lambda over n to find the film wavelength. Because what we're caring about is how is the wavelength like happening in here relate to the path length, and we can solve for that. And then looking at this last part, they're talking about this coming at an angle to the normal. And we've kind of not talked about that actually at all. Here we've kind of assumed everything's normal in all these examples. And, with Snell's law, when the angle to the normal is 0, everything's kind of going to be nice and normal. But where are we? Here. But with this, we're going to get some angle, so it's not going to be vertical, it's going to be some angle, which means the path length increases. And if the path length increases, then the wavelength has to increase to compensate. And this formula is kind of the same that we worked with above. All right, I think that's everything. Yeah, again, let me know if you have any more questions about that. If you have the chance, you could check in with your teacher about this second question. Because I think it is definitely dependent on the wavelength. Because the difference between constructive and destructive interference is not wavelength independent. It has to be it's that wavelength that determines it. All right, I think that's everything. Again, let me know if you have any questions, and I guess I'll stop it all here.